Welcome to the Deep Dive. We're here to plunge into some really complex topics and try to distill them into something genuinely fascinating, maybe even actionable for you. Today, we're tackling something huge, one of the most ambitious and frankly pretty mind-bending quests in 21st century physics. We're talking about unifying the two, well, titans of modern science, Einstein's general relativity and the standard model of particle physics. I mean, each of these theories, they're just monumental achievements, right? Incredibly successful. General relativity, for instance, it completely changed how we see gravity. The whole cosmos, it paints this picture of the universe not as some fixed stage, but, dynamic, a malleable geometry. Space-time itself isn't just a backdrop. It bends, it stretches, it warps, and that warping is gravity. It tells planets how to orbit stars, how light bends the whole large-scale structure. But then you look across this huge conceptual gap, and there's the standard model, and that's a quantum field theory.
And it describes with truly breathtaking precision the fundamental particles, all matter, and the three forces, strong, weak, electromagnetic, that govern how they interact. But here's the catch, right? The standard model, as it stands now, it operates against a fixed, unchanging geometric background. It just assumes a flat, static space-time, a stage that doesn't really participate. You see the tension. It's fundamental. One theory says geometry is dynamic, it is gravity. The other says, nope, geometry is fixed. It's just where the quantum stuff happens. So our mission today, for you, our listener who's, intellectually curious, is to arm you with the conceptual toolkit you need to even start thinking about bridging this gap. Because frameworks like, say, Dr. Eric Weinstein's geometric unity, which is this powerful, super ambitious proposal for unification, they're written in a very specialized language. Elegant, sure, but often unfamiliar. To really get the essence, we first need to become, reasonably fluent in the essential grammar they use. Differential geometry. So think of this deep dive as your personal primer. We've tailored it. We're taking your notes, the core ideas of differential geometry, and we're going to build up from the intuitive stuff to the more abstract. In this journey, it's really aimed at those of you who are maybe STEM professionals. You've got a solid handle on calculus, maybe differential equations, linear algebra, but perhaps these more specialized areas, like differential geometry itself, are new territory. We're going to guide you through this complex, but honestly, incredibly beautiful mathematical landscape. We want to make sure you don't just hear the terms, but really grasp their power and, their connection to the universe's deepest mysteries.
That's absolutely right. It's profoundly true. Without really understanding this language, a lot of the cutting edge of theoretical physics, especially where these huge ideas might finally meet, it just stays locked away, inaccessible. And this isn't just, abstract math for its own sake. It really is the grammar of the universe. It's the precise vocabulary physicists need to describe reality at its most fundamental level, way beyond our everyday sort of flat perceptions. It's a language that lets us talk about worlds where space itself can stretch and contract and twist in ways that are hard to picture initially. And that brings up a really critical question, doesn't it? How exactly do we bridge that gap? How do we get from our familiar, flat space math, the stuff we learned in school, to this dynamic curved reality that modern physics describes? We're just so used to Euclidean geometry. Parallel lines stay parallel, triangle angles add up to 180. But the universe, especially on cosmological scales, or say near a black hole, it just doesn't play by those rules. So yeah, we'll break this challenge down step by step, laying the groundwork so you can really appreciate the elegance and, frankly, the sheer necessity of these mathematical ideas.
All right, let's dive in then. Let's unpack this journey into differential geometry. And it really starts with the most fundamental object, the manifold. The core idea here, the big conceptual leap, is to generalize all those familiar calculus operations, differentiation, integration, vector fields, all that from the flat spaces we're used to, like Rn, Cartesian coordinates. Spaces that are fundamentally curved. I mean, just imagine trying to figure out the shortest path between 2 points, or how temperature changes, not on flat graph paper, but maybe on the surface of a crumpled sheet, or some complex 3D shape. That's the kind of problem differential geometry is built to solve. So what is a differentiable manifold? At its heart, a manifold is a space that, if you zoom in really close locally, it looks just like our familiar flat environment, Rn. Think about the Earth's surface. Globally, we know it's a sphere, it's curved, no accretion. But if you're standing in a field, say, that small patch of ground right around you seems, for all practical purposes, completely flat. You can use regular coordinates towards south, east, west, map out your surroundings pretty accurately. Almost like you're on an infinite flat plane. And this locally flat property, that's the absolute key, because it's precisely what lets us adapt and use all our existing calculus knowledge, derivatives, integrals, vectors, all the stuff we mastered in flat space on these curved spaces. It's the bridge, really. It connects the familiar to the geometrically exotic. Lets us use our powerful tools even when the territory looks strange. Now, to make this locally flat idea rigorous, mathematically sound, geometers use things called charts and atlases. A chart is basically a map. It's a mathematical function, right? It takes a small piece of the manifold and smoothly transforms it, flattens it out onto a piece of standard Euclidean space, like Rn. It's like putting a local coordinate grid on that little patch. Imagine carefully peeling a small bit of orange peel and trying to flatten it without tearing it. It's kind of like a chart. Each piece gets its own coordinates. But obviously a single chart probably won't cover the whole manifold without messing things up, distorting distances or angles, or just being incomplete. Like one flat map can't show the whole Earth accurately.
So you need an atlas. And an atlas is just a collection of these charts that all together manage to cover the entire manifold. Just like a geographical atlas uses multiple flat maps for different regions, right? And they overlap at the edges. And here's the crucial detail, the absolute must-have for doing calculus. These charts must overlap smoothly. The transition between one chart's coordinate system and another's has to be differentiable, smooth. So if you're navigating using one map and crossed into the area of another, the coordinates, the distances, everything needs to line up perfectly smoothly. No jumps, no kinks. This ensures that when we do calculus, like taking a derivative, we get consistent results. Geometrically meaningful results no matter which local chart, which coordinate system we happen to be using at that moment.
That's a really clear way to put it. And the profound implication here, is how this idea of local flatness, made rigorous with charts and atlases, lets us harness all that calculus knowledge we already have. It's not about inventing some totally new calculus for every different curved space. It's more like saying, look, we can still use our familiar tools. We just need to be really, really careful about how we move between different patches, different charts on our curved space. This machinery, the charts, the atlases, the smooth overlaps, it provides the necessary rigor. It makes these transitions seamless. It guarantees our calculations are independent of the specific coordinates we happen to pick. And that coordinate independence, well, that's just fundamental in physics, isn't it? If a physical law changes based on how you decided to draw your grid lines, it's not a real law of nature. So this framework lets us define things intrinsically on the manifold itself, reflecting its true geometry, not just some artifact of our mapping choices. It shifts the focus from describing where something is to describing what it is within the space itself.
Okay, so we've got these manifolds, these spaces that are locally flat, covered by this atlas of smooth charts. We can picture curved surfaces now. But if we're just at a single point P on this, let's call it a curved canvas, how do we even talk about direction or velocity or a path that's part of the surface itself without having to imagine it sitting inside some bigger external space? And this brings us to the next really crucial idea, the tangent space. This is where it gets really interesting, actually, because it gives us the local linearization we need for calculus. At every single point P on a manifold, M, we can define something called the tangent space at P, often written TPM, right? So the tangent space at a point P, what is it? It's essentially the best flat linear approximation of the manifold right at that specific point. You can picture it maybe as a flat plane that just kisses the curved surface at that one spot, perfectly matching its local slope or orientation. All the infinitesimal action, all the local calculus, happens in this space. It's the space containing all possible velocities, or you could say directional vectors, for any smooth path you could imagine passing through that point P. Think of, I don't know, a tiny bug crawling on a sphere. At any instant, its velocity vector, which way it's going, how fast that vector lives in the flat plane that's perfectly tangent to the sphere right where the bug is. And crucially, this tangent plane is different for every point on the sphere. But it lets us use our linear algebra intuition vectors, dot products, etc., locally, point by point, even on this curved world. Now, visualizing that plane, touching a sphere, that's a great starting point, super intuitive. But the most powerful definition is the really rigorous one in differential geometry. Is purely algebraic. It says a tangent vector is a derivation. Okay, what does that mean maybe for someone who knows derivatives? Well, it's an operator, like a set of instructions. It takes any smooth function defined on the manifold, say temperature, and it tells you the rate of change of that function. It's a directional derivative in one specific direction at that point. So a tangent vector isn't just an arrow you draw.
It's actually a mathematical operation that measures change along a direction. And this intrinsic definition based on derivations is incredibly important because it means we don't need to imagine our universe floating inside some higher dimensional flat space, which is often, an unnecessary assumption, maybe even misleading. In general relativity, our universe is the manifold. It doesn't need to be embedded in anything else. We're defining these directions purely from within the manifold's own structure. And just building on that quickly, a vector field. That's simply a smooth way of assigning one of these tangent vectors to every single point on the manifold, like mapping the velocity vectors of water flowing over a surface, right? Each point has a direction and speed associated with it.
Exactly. And it's precisely this intrinsic approach using derivations that really answers that critical question. How do you define direction or rate of change on a curved surface without needing some external flat reference frame? The tangent space, especially through this really elegant idea of a derivation, it gives us an incredibly self-contained intrinsic answer. It effectively linearizes the curved world, but only locally at each point. It lets us point in meaningful directions that are totally independent of any coordinate system we might choose to slap onto it. This algebraic definition is just so powerful because it frees us from needing these external embedding spaces. It makes the whole description of curvature, of motion, completely self-contained within the manifold itself. It lets us do the essential calculus operations, finding slopes, directions of change, even though the whole space is fundamentally curved. It's like the first major step towards really thinking about geometry from the inside out.
Okay, so now we have manifolds, these locally flat spaces, and we have tangent spaces at every point, giving us intrinsic directions. The next logical step, the absolutely necessary one, is how do we start measuring things? How do we quantify distance along a path, or the length of a vector, or the angle between two vectors in one of these tangent spaces? Because, a bare manifold, even with tangent spaces defined everywhere, it doesn't inherently have any concept of these basic geometric properties. It's just a collection of points structured smoothly. The solution, and it's really elegant, is we have to equip the manifold with something called the Riemannian metric, usually denoted by the symbol G. What is it? Well, the metric is essentially a rule. It's a mathematical object that, at every single point on the manifold, defines an inner product, or you can think of it as a dot product. It generalizes that familiar operation on the tangent space at that point. Remember how the dot product in flat Euclidean space lets you calculate vector lengths and the angles between them? Well, the Riemannian metric does exactly that, but it does it locally at every point on our potentially curved manifold. It provides the tool for local measurement. Now, in local coordinates, the metric gets represented by a set of numbers, usually arranged in a matrix, or more accurately, a tensor. This is the famous metric tensor, written as G mu nu. This thing is absolutely foundational in GR and differential geometry. Its components directly tell you the local geometry, how distances are measured right there. And this tensor lets us calculate the infinitesimal distance, ds, for any tiny step we take on the manifold. It's a direct, powerful generalization of Pythagoras' theorem. So instead of just ds2 dx2 plus d psi, like on a flat plane in a curved space with a metric, it becomes ds2 gx2 dx. For those used to tensor notation, that implies summing over the repeated indices key dk. We're summing up all combinations of coordinate steps, ds key, weighted by the appropriate component of the metric tensor, g, and the impact of defining this metric. It's huge. Once you specify a metric, the manifold transforms. It goes from being just an abstract topological space to a full-fledged geometric space. We can now actually measure the lengths of curves, paths drawn on the surface. We can measure the angles between tangent vectors at any point. And here's the direct, really mind-blowing connection to physics. In general relativity, the metric tensor is the gravitational field. That's it. Its components, the G values, are exactly what we solve for in Einstein's field equations. They tell us precisely how space-time is curved by mass and energy, and how that curvature dictates gravity's influence on everything.
It's truly humbling, isn't it, to think that the very stretchiness and squishiness of space and time, which we experience as gravity, is mathematically encoded in something as, relatively compact as a tensor. The Riemannian metric isn't just some abstract mathematical tool. In Einstein's theory, it really is the fabric of space-time. Its components, the key, they literally dictate how we measure distance and time duration and how gravity warps those measurements. It's the physical embodiment of the space itself. It gives you a local ruler and protractor at every single point. Imagine trying to use a map that has no scale bar, no way to measure distances or angles accurately. That's kind of like a bare manifold. The metric is that scale, that ruler. It lets us quantify the local geometry, understand how lengths and angles behave locally. It's the absolutely essential ingredient that turns an abstract space into a physically meaningful geometry. A geometry where concepts like shortest path or time elapsed along a trajectory are rigorously defined and actually measurable. Without the metric, general relativity just wouldn't be possible.
Okay, so with distance and angles now precisely defined by this Riemannian metric, we're ready for what feels like the next big conceptual hurdle, doing full calculus, specifically differentiation, on these curved landscapes. And this leads us to a concept that might seem a bit abstract at first, but it's absolutely vital for making sense of curved spaces. It's called the covariant derivative. All right, so we want to differentiate a vector field. Easy enough in flat space, right? But it turns out this is a key challenge on a curved manifold. The reason really gets to the heart of curvature. Why is it hard? Because the tangent spaces themselves, and therefore the local coordinate systems we might use, they change from point to point. If you have a vector field, maybe wind velocity over the Earth, and you move from point A to point B, you can't just compare the coordinate components of the wind vector at B directly to the components at A. Why not? Because the very basis vectors of your coordinate system, your north or east directions, might have actually changed direction relative to the underlying surface as you moved. So the simple partial derivative of a vector's components, the way we learned it in multivariable calc, it turns out it's not a well-defined geometric object on a curved space. Its change gets mixed up, polluted, you could say, by the change in the coordinate system itself. It's like trying to compare the vector pointing up in London to the vector pointing up in Buenos Aires. They point in physically different directions in 3D space, but in their local coordinate systems, they might both just be represented as, say, 0, 0, 1. We need a way to compare vectors that accounts for the curve. The solution, the really elegant fix, is to introduce something called a connection. A connection provides a strict mathematical rule for what's called parallel transporting a vector. This means moving a vector along a path from one point to a nearby one while keeping it pointing in the same direction relative to the geometry, no matter how your chosen coordinates might be twisting or turning underneath. It sounds subtle, but it's fundamental for defining derivatives that are truly intrinsic to the manifold's geometry, not just artifacts of our coordinate choice. And the mathematical operator that actually performs this coordinate-independent differentiation, that's a covariant derivative, usually written with H symbol, nabla. In local coordinates, this connection gets defined by a set of coefficients numbers that depend on your position called Christoffel symbols, named after Elwin Christoffel. These symbols are precisely the correction terms needed to make the derivative work properly. They account for how the coordinate basis vectors themselves change as you move, ensuring that your derivative measures the genuine change in the vector field, not just the change in your ruler. It lets us do calculus properly on curves.
Yes, and this whole challenge, this seemingly technical problem of how to define a meaningful derivative for a vector field on a curved manifold, that's exactly what drove the development of the covariant derivative. It's really a testament to the ingenuity of mathematicians, people like Riemann, Ricci Cabastro, Levi-Civita, to figure out a way to compare vectors that inherently live in different tangent spaces. It guarantees that our calculations are intrinsic, that they reflect the actual geometry and aren't just some random artifact of the coordinates we happen to choose. I mean, without the covariant derivative, any attempt to do calculus on curved spaces would just fall apart into coordinate-dependent confusion. You'd get different answers depending on how you drew your map. It's the sophisticated mathematical engine that allows us to rigorously generalize concepts like rate of change and parallelism from the comfort of flat Euclidean space to the complex dynamic geometry of spacetime itself. It truly frees us from coordinate artifacts and lets us speak the real language of the curved universe.
That makes sense. This connection idea sounds really powerful for defining derivatives. But you might wonder, could there be many different ways to define such a rule? Many possible connections? Well, for any manifold that has a metric, remember that gives us distances and angles, making it a Riemannian manifold, it turns out there is a unique and completely natural choice of connection. This very special connection is called the Levi-Civita connection, named after Tullio Levi-Civita. And it's unique because it's the only connection that satisfies two really important and actually quite intuitive properties. First, it has to be compatible with a metric. What does that mean? It means that lengths of vectors and angles between vectors are perfectly preserved when you parallel transport them using this connection. If you take a vector and slide it along a path using the Levi-Civita connection, its length won't change, and the angle it makes with any other vector also being parallel transported stays the same. That feels right physically. If you slide an arrow on a surface without stretching or twisting it, its length shouldn't change. Second, it has to be torsion-free. This is a bit more technical, but intuitively it means that infinitesimal parallelograms close up properly. Imagine taking a tiny step in direction X, then a tiny step in direction Y. Then you try to come back by taking a tiny step in direction X, and then FHY. If the connection is torsion-free, you end up exactly back where you started, even on a curved surface. There's no extra twist introduced by the connection itself. And here's the truly profound theorem. Once you define how to measure distance using the metric tensor, the rule for differentiation, the Levi-Civita connection, is automatically uniquely fixed. It just pops out. You don't get to choose it.
It emerges naturally, inevitably, from the metric itself. That's a deep connection between measurement and differentiation. Okay, so with this unique natural connection at hand, we can finally define one of the most important concepts in both differential geometry and physics: geodesics. A geodesic is, simply put, the straightest possible path on a manifold. It's the path a particle would naturally follow if no external forces were acting on it, besides the force of the geometry itself. Mathematically, a geodesic is defined as a curve that parallel transports its own tangent vector, meaning, as you move along the curve, the direction vector pointing along the curve is considered constant relative to the underlying geometry, according to the Levi-Civita connection. Even if the path looks curved from some outside perspective, like a great circle on a sphere, think of the shortest flight path between London and Tokyo, it is the straightest possible path on the sphere's curved surface. And here is the absolutely profound link to general relativity. This is a cornerstone of Einstein's theory. Particles that are in free fall, subject only to gravity, travel along geodesics of spacetime. Their paths are determined entirely by the curvature of spacetime, defined by the metric, not by some force pulling them in the old Newtonian sense. Objects aren't being pulled by gravity. They are simply following the straightest possible lines available to them in the curved spacetime they inhabit. They're following the contours, the geodesics, of warped geometry.
That coherence is just stunning, isn't it? The link between how you measure things, how you differentiate things, and how you define straightness. The existence of this unique Levi-Civita connection really shows this deep mathematical unity. Measurement defines differentiation, which in turn defines the straightest paths. And that conceptual chain, that logic, is the absolute bedrock of how general relativity reimagines gravity. It's not a force acting across space, it's a manifestation of space-time curvature itself. Particles aren't pulled, they just follow the most natural path, the shortest path in a way, through curved space-time, and that path is a geodesic. This insight completely revolutionized how we think about gravity. It went from being an interaction between objects to being an inherent property of the space-time continuum itself. It's just an incredibly elegant and unified view of what gravity fundamentally is.
Right, we've really built up quite a toolkit now. We have manifolds for our spaces, tangent spaces for directions, the metric for measuring, the covariant derivative for differentiating properly. Now, finally, the grand reveal, the payoff. How do we actually quantify, measure, how much a manifold deviates from being flat? How do we put a number, or rather a whole set of numbers, on its curvedness? This brings us to the absolute heart of geometry: curvature itself. The core idea is that curvature is the fundamental, intrinsic measure of how a manifold is not flat. And all of this information, all the ways it can curve and twist, is completely captured by one incredibly powerful, though complex mathematical object, the Riemann curvature tensor, usually denoted R. Now, this tensor is intricate. It has many components. In 4D spacetime, it has 256 components initially. Those symmetries reduce that number significantly. But we can understand its essence, its meaning, in two key ways that also reveal its physical importance. First way, the Riemann tensor measures a failure of covariant derivatives to commute. Remember how in flat space, taking partial derivatives in different orders gives the same result? X-ray is the same as S-crete. Well, in the curved space, that's generally not true for covariant derivatives. If you take two covariant derivatives, say x and hy, representing derivatives along vector fields x and y, and apply them one after the other to some vector field z, the result you get from doing x first, then xy, so x, y, z, will generally be from doing xy first, then x, so x, y, z, it's x. The Riemann tensor is precisely the thing that measures this difference. It quantifies this non-commutativity. Schematically, r, x, y, z, x, y, z, x, y, z, minus a term involving the Lie bracket of x and y if they aren't coordinate directions, but let's keep it simple. On a perfectly flat space, this difference is always zero. The Riemann tensor is zero. On a curved space, it's non-zero, and its components tell you exactly how and in what way the derivatives fail to commute, revealing the underlying curvature. Okay, the second way to understand the Riemann tensor, maybe even more intuitive, is through the failure of parallel transport around a closed loop. It measures how much a vector rotates, how its direction changes, when you parallel transport it all the way around a small, closed loop on the manifold. Let's go back to the sphere example. Imagine you're at the North Pole, holding an arrow pointing, say, towards Greenwich. Now, parallel transport it down to the equator along that line of longitude. Once you're at the equator, turn 90 degrees right, eastward, and parallel transport the arrow along the equator for, say, a quarter of the way around the Earth. Then turn 90 degrees right again, northward, and parallel transport it straight back up to the North Pole along that new line of longitude. When you get back to the North Pole, guess what? Your arrow will not be pointing towards Greenwich anymore. It will have rotated by exactly 90 degrees relative to its starting direction.
This change in direction after completing a closed loop, this holonomy, is a direct, measurable effect of the sphere's intrinsic curvature. The Riemann tensor is what quantifies this rotation for any infinitesimally small loop. If you did the same thing on a flat piece of paper, your arrow would come back pointing exactly the same way. 0 Riemann tensor, 0 rotation. And in physics, the Riemann tensor has a very direct, very physical meaning. It describes tidal forces. Tidal forces are the relative accelerations experienced by nearby objects that are both freely falling in a gravitational field. Think about the classic, slightly gruesome image of an astronaut falling feet first towards a black hole. Because the gravitational pull is stronger, closer to the singularity, their feet are pulled harder than their head. This difference in pull causes a stretching force along their body. At the same time, every part of their body is being pulled towards the central point. So parts of their body slightly to the left or right of the center line get pulled slightly inwards towards each other, causing a squeezing force across their body. This stretching spaghettification and squeezing, this relative acceleration and distortion of objects, it's a direct result of the non-uniformity of the gravitational field. And that non-uniformity is curvature. That's what the Riemann tensor describes. It shows how gravity manifests geometrically. Nearby objects don't just fall together, they accelerate relative to each other because the field isn't uniform. The Riemann tensor nails this mathematically.
Absolutely, and this discussion around the Riemann tensor really brings home the answer to that crucial question. What's the real, tangible impact of having a curved geometry? The Riemann tensor is that answer. It shows us that curvature isn't just some abstract mathematical notion. It has direct, measurable, sometimes even destructive physical consequences. We see it in those tidal forces that would rip apart something falling into a black hole. We measure it precisely in the way light paths get bent when they pass near massive objects like the sun gravitational lensing. And ultimately, it governs the expansion and evolution of the entire universe. It's the very fingerprint of gravity, encoded directly into the geometry of spacetime. It's not some mysterious force acting at a distance. It's a measurable distortion of reality's fabric that dictates how objects move relative to each other. It's the ultimate description of how our universe deviates from being simple, flat, and static.
Okay, so we've spent a good amount of time building up this whole geometric framework. We have manifolds, tangent spaces, metrics, connections, curvature. The whole language for describing curved spaces like spacetime. Now, let's pivot slightly. Let's explore the powerful algebraic structures that are essential for understanding symmetries, because symmetries are absolutely critical, especially for understanding particles and forces in the Standard Model. This takes us a bit beyond pure geometry into what you might call the algebraic scaffolding of modern physics. So, moving beyond just the shape of space itself, let's talk symmetries. Continuous symmetries think about rotation, like a sphere looking the same no matter how you turn it, or the laws of physics being the same yesterday as today, or here versus over there. These are incredibly important in physics, and they are described mathematically by objects called Lie groups. Remember, pronounced Lie, like the name. Okay, so what exactly is a Lie group? It's a really fascinating mathematical beast because it's two things at once. It's a group in the algebraic sense, meaning it has elements. You can combine them, like doing one rotation then another. There's an identity, doing nothing, and every element has an inverse. You can undo any rotation. And at the same time, it's also a smooth manifold. It has all those geometric properties we just discussed. It's locally flat, differentiable. You can do calculus on it. Think about all possible rotations in 3D space. You can combine any two rotations to get a third one. That's the group part. And the set of all possible rotations itself forms a continuous smooth space, a manifold, though it happens to be a curved one, SO3. It's this seamless blend of algebra and geometry that makes Lie groups so powerful for describing symmetries. Now, the truly profound insight of Lie theory, developed by Sophus Lie, is that you can understand the essential local structure of a potentially complicated Lie group by looking at something much simpler. A linear object called its Lie algebra. What is the Lie algebra? It's literally just the tangent space of the Lie group at its identity element. Remember tangent spaces. It's the flat approximation of the group manifold right at its origin or neutral element, like the no rotation state. So instead of grappling with the possibly complex, curved, nonlinear structure of the whole group, we can zoom in on its origin and study its linear approximation, the Lie algebra, which is just a vector space. And this Lie algebra comes equipped with a crucial operation called the Lie bracket. For Lie groups represented by matrices, this bracket is usually just the commutator, xy equals xyyx. What does the bracket tell you? It measures how two infinitesimal transformations, two tiny steps away from the identity in the Lie algebra, fail to commute. If you do tiny step x, then tiny step y, is that the same as doing y then x? The Lie bracket quantifies the difference. And the really amazing part is that by studying this linear Lie algebra and its bracket structure, you can reconstruct and understand a huge amount about the complex, nonlinear global structure of the original Lie group. This linearization is a massively powerful tool for studying continuous symmetries. In physics, this is absolutely central. The standard model of particle physics, as we mentioned, is fundamentally a gauge theory. What that means is that the fundamental force is electromagnetism, the weak force, the strong force they actually emerge from, demanding that the laws of physics obey a particular local Lie group symmetry. Local here is key. It means the symmetry transformation can be different at every single point in spacetime. That's a very strong requirement. Specifically, the standard model is built on the Lie group SU3, SU2, SU2. SU3 gives rise to the strong nuclear force, quantum chromodynamics. SU2 is related to the weak nuclear force. And U1 corresponds to electromagnetism. The very existence, the nature, the properties of these forces are, in a deep sense, consequences of imposing these abstract mathematical symmetries locally everywhere. It's just a stunning connection between abstract algebra and the concrete forces governing our universe.
It really is astonishing, isn't it? Lie groups and Lie algebras, they genuinely form the mathematical backbone of the standard model. They provide the exact framework needed to understand how these fundamental forces pop out of symmetry principles. And that gauge principle, the demand that physics looks the same, even if you apply these symmetry transformations independently at every point in spacetime, it doesn't just describe the forces. It actually dictates their existence and their essential character, how they couple to matter, what mediating particles they must have, like photons, W and Z bosons, gluons. It's a truly compelling example of how these abstract mathematical structures directly manifest themselves as observable physical reality. It tells us symmetries aren't just, convenient ways to classify things. They are profoundly prescriptive. They tell us what forces must exist and how they must behave according to the chosen symmetry group. That's why understanding Lie theory is just non-negotiable if you want to dig into particle physics and fundamental interactions. It really is the language of forces.
Okay, so we've seen how symmetries via Lie groups and algebras are behind the fundamental forces. But what about matter itself? Specifically, what about fundamental particles like electrons or quarks, which have this really strange quantum property called spin? Now, the mathematical objects we've talked about so far, vectors, tensors, components of the metric, etc., they're great for describing lots of physical things. Momentum, forces, fields, stress in a material. But remarkably, they're not sufficient to describe these fundamental matter particles like electrons, positrons, quarks. They're described by a completely different class of mathematical objects called spinors. Remember, pronounced spinors. What's the defining characteristic of a spinor? It's their truly weird, really counterintuitive behavior when you rotate them. A spinor object has to be rotated a full 720 degrees, that's 2 complete turns, 2 full circles, to get back to its original mathematical state. A normal 360-degree rotation, which brings any everyday object or even a vector back to where it started, actually flips the sign of a spinner's quantum state. It makes it negative. This property seems bizarre, right? How can something need 2 full turns to return to itself? But this seemingly strange behavior finds its perfectly natural mathematical home in another powerful algebraic structure called Clifford algebra, named after William Kingdon Clifford. So what's a Clifford algebra? Well, fundamentally, it's an algebra that you build starting from a vector space that already has a metric defined on it. So it inherently knows about the geometry, about distances and angles from the get-go. And the crucial thing it does is define a new kind of multiplication, a single operation called the geometric product. This product is incredibly elegant because it fuses together 2 operations we often treat separately in linear algebra. The dot product, or inner product, which gives you a scalar, just a number, and the wedge product, or outer product, which gives you something called a bivector, representing an oriented plane or area element. So for any 2 vectors, u and v, in this algebra, their geometric product is simply u of v plus u bz. It combines the scalar part and the plane part into one single algebraic object. This algebra automatically contains the rich geometric information of the space. It lets you represent not just vectors, lines, but also planes, volumes, and higher dimensional elements naturally within one unified algebraic framework. It's a more complete description of geometry than just vectors alone. Now, here's the key connection. Within any Clifford algebra associated with a space, like Euclidean space or Minkowski spacetime, you can mathematically construct a special group called the spin group, often written spin. And this spin group is what's known as the double cover of the ordinary group of rotations in that space, like SO3 or SON. What does double cover mean? It means for every single rotation or everyday world, like, say, rotating 90 degrees around the z-axis, there are actually two distinct elements in the spin group that correspond to that same physical rotation. It's like having two different paths in the spin group that both end up producing the same net rotation in physical space. It's this 2-to-1 mapping, this double cover property, that perfectly captures the 720-degree symmetry required by spinors. And so spinors are precisely the fundamental mathematical objects that this deeper, more complete spin group naturally acts upon. They are the most basic things that transform correctly under the spin group, not just the rotation group. This reveals this really profound hierarchy, doesn't it? You start with a metric, defining geometry, that gives rise to a Clifford algebra, a richer algebraic description, which contains within it the spin group, the true rotation group, and the natural things that group acts on are spinors. This is incredibly powerful. It tells us that spinors, and their weird quantum spin, aren't just some random odd feature tacked onto physics. They're an inevitable consequence of seeking a truly complete and consistent algebraic description of geometry itself. They are deeply intrinsically linked to the geometric and algebraic structure of spacetime.
It is a remarkable revelation, absolutely. Spinors, which seem so bafflingly counterintuitive at first glance with that 720-degree rotation thing, they turn out to be a natural, almost unavoidable consequence when you demand more complete algebraic language for geometry. And the implication is profound. It suggests that the very existence of fundamental matter particles having this property called spin isn't some arbitrary choice made by nature. It seems to be deeply woven into the very fabric, the geometric and algebraic structure of spacetime itself. It leads towards a really deep unification of geometry and matter right at the foundational level. It's a beautiful example of how these seemingly abstract mathematical structures, like Clifford algebras, provide exactly the right framework to describe even the most fundamental and frankly weird aspects of physical reality. It's not just a clever mathematical trick. It feels like a deep insight into the intimate connection between the geometry of our universe and the intrinsic properties of the matter within it. It really hammers home that reality at its deepest level speaks this combined language of geometry and algebra.
So after this, pretty deep dive into differential geometry and related algebra, what does this all mean for that grand challenge we started with unifying physics? We've seen how Einstein's general relativity, our best theory of gravity, is meticulously built on this idea of a dynamic metric tensor living on a 4D manifold. That framework describes spacetime itself as this flexible, evolving fabric where gravity is the curvature. That's the language of the cosmos, the very large scale.
Right. And then, as we discussed, the Standard Model, our incredibly successful theory of particles and the other forces, is constructed quite differently. It's built on imposing a Lie group symmetry, that SU3, SU2, AU1, which acts on spinor fields representing matter. But crucially, these spinor fields, describing electrons, quarks, and so on, they don't live directly in the spacetime manifold in quite the same way the metric does. Technically, they live in an auxiliary mathematical space, what mathematicians call a fiber bundle, that's sort of conceptually attached or built over each point of the space-time manifold. So we're left with this situation that people sometimes call the twin origins problem. Why does nature seem to have these two fundamentally different geometric starting points? One for space-time itself, coming from the metric tensor, and another seemingly separate one for particles and forces, coming from these abstract gauge groups acting on spinors in these fiber bundles? It feels like there are two separate foundational rulebooks for the universe, and that leaves this rather unsatisfying conceptual gap between gravity and the quantum forces.
Exactly. And this twin origins problem is precisely the kind of deep issue that a theory of geometric unity, like the ambitious framework proposed by Dr. Eric Weinstein, really aims to tackle head-on. The goal is to resolve this fundamental dichotomy. How? By proposing that both the metric of spacetime, gravity, and the gauge symmetries of particles, forces, and matter can be derived not from two separate places, but from the intrinsic geometry of a single, richer, underlying mathematical object, and use exactly the kind of sophisticated mathematical language we've just spent our time trying to unravel: manifolds, connections, curvature, Lie groups, spinors, maybe even Clifford algebras more centrally. It uses these tools to try and construct a single comprehensive framework, a framework where the fundamental properties of our universe, why we have gravity, why we have these specific forces, why particles have spin, maybe even why we have 3 generations of particles aren't just chosen by hand, aren't arbitrary inputs or separate rules. Instead, the hope is they emerge as necessary, almost inevitable consequences of some deeper unified geometric principle.
The idea is to find one fundamental mathematical structure or principle from which all the known physics of our universe just naturally, elegantly flows out. It's worth taking a moment to just consider how these abstract mathematical ideas, taking us from flat intuition to curved reality and rich algebraic structures, might fundamentally reshape our very understanding of what reality is made of. This journey, from thinking about flat space to trying to grasp the aims of something like geometric unity, is clearly one of profound and ongoing discovery, isn't it? So, what new questions does this primer spark for you about the universe's deepest, most tangled secrets? And how might these very mathematical concepts pave the way for a unified physics that goes beyond our current, albeit incredibly impressive, understanding?